Article 230.42b states that the minimum ampacity of ungrounded conductors for specific installations shall not be less than the rating of the service disconnecting means. Article 240.4b provides an exception, allowing conductors with ampacity less than the rating of the overcurrent protection to be used only for specified types of installations, including service entrances, where the conductor is protected by a circuit breaker or fuse rated not higher than the ampacity of the conductor. Let's consider a scenario with a 400 amp service disconnecting means and two conductor options. Firstly, using 600 kcmil conductors with an ampacity of 400 amps would comply with 230.42b. This is because the ampacity of the conductors is equal to the rating of the 400 amp service disconnecting means. Secondly, using 500 kcmil conductors with an ampacity of 380 amps would comply with 240.4b. These conductors are being used for a service entrance and are protected by a 400 amp circuit breaker, which is not greater than the conductor's ampacity. Both the 500 kcmil and 600 kcmil conductors are permitted for use as service entrance conductors based on the interpretation of these code requirements. However, there are additional considerations. Firstly, voltage drop. When selecting conductors for service entrances, it is important to consider voltage drop and ensure that the conductor size is sufficient to maintain acceptable voltage levels throughout the installation. Secondly, local regulations. Local jurisdictions may have additional requirements regarding the conductor size and overcurrent protection for service entrances. It is always advisable to consult with the local authority having jurisdiction for specific guidance. In this case, both conductor options technically meet the minimum NEC requirements. However, selecting the best option involves considering other factors. Using 600 kcmil conductors provides additional ampacity beyond the minimum requirement, which may be beneficial if there are plans to increase the service load in the future. It also ensures that the conductor ampacity always meets or exceeds the service disconnect rating, simplifying compliance with 230.42b. Using 500 kcmil conductors is permissible under the exception in 240.4b, which allows for the overcurrent protection device to be rated higher than the conductor ampacity in certain situations. However, this exception only applies to specific installations such as service entrances and requires careful consideration of the conductor's ampacity and the overcurrent protection device rating. The decision between 500 kcmil and 600 kcmil conductors ultimately depends on the specific requirements of the installation, including the anticipated load, voltage drop considerations, and local regulations. It is essential to consult with a qualified electrical engineer or inspector to ensure that the selected conductor size meets all applicable code requirements and provides adequate capacity for the intended use. Let's delve into the specific articles of the National Electrical Code or NEC relevant to this discussion, providing a detailed explanation of their requirements. Article 230 covers service entrances, outlining the rules for the conductors that bring power from the utility to the building. This article is crucial for ensuring the safety and reliability of the electrical system. Article 230.42 specifically addresses the minimum size and ampacity of service entrance conductors. It states that the conductors must have an ampacity sufficient to carry the calculated load, as determined by Article 220, and must not be smaller than specified in 230.42a on ATWO or B. The key part of 230.42b states that the minimum ampacity of ungrounded conductors shall not be less than the rating of the service disconnecting means. This means that if the service disconnecting means, such as a main breaker, is rated at 400 amps, the service entrance conductors must have an ampacity of at least 400 amps, unless specific exceptions apply. Now let's move on to Article 240, which covers overcurrent protection. This article provides the requirements for protecting conductors and equipment from overcurrent conditions such as short circuits and overloads. Article 240.4b is an exception to the general rule that conductors must be protected to their ampacity. This exception allows the next higher standard overcurrent device rating to be used, provided certain conditions are met. Firstly, the conductors must be part of a specific installation, such as a service entrance, feeder, or branch circuit. Secondly, the overcurrent device must not exceed the next higher standard rating above the conductor's ampacity. Thirdly, the conductors must be protected against overload conditions. The exception in 240.4b is often used in service entrance applications where the available standard overcurrent device rating is slightly higher than the conductor's ampacity. For example, if a conductor has an ampacity of 380 amps, it can be protected by a 400 amp circuit breaker, which is the next highest standard rating. However, it's important to note that this exception should only be used when the conductor is adequately protected against overload conditions and the installation meets all other applicable code requirements. When applying these code requirements to the specific scenario of selecting service entrance conductors for a 400 amp service, there are a few key considerations. Firstly, determine the calculated load. The service entrance conductors must be sized to carry the calculated load as determined by Article 220. This calculation takes into account all of the connected loads in the building, including lighting, receptacles, appliances, and any other electrical equipment. Secondly, consider the ampacity of the conductors. The conductors must have an ampacity sufficient to carry the calculated load and must not be smaller than specified in 230.42b. In the case of a 400 amp service, the conductors must have an ampacity of at least 400 amps, unless the exception in 240.4b applies. Thirdly, evaluate the overcurrent protection requirements. The conductors must be protected against overcurrent conditions in accordance with Article 240. If the conductors have an ampacity less than 400 amps, the exception in 240.4b may be used, provided the conditions are met. Fourthly, account for voltage drop. The conductors must be sized to minimize voltage drop, ensuring that the voltage at the load is within acceptable limits. Voltage drop can be a significant factor in service entrance applications, especially for long runs of conductors. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. When selecting between 500 kcmil and 600 kcmil conductors, it's important to compare their ampacity and voltage drop characteristics. 500 kcmil copper conductors typically have an ampacity of around 380 amps at 75 degrees Celsius, while 600 kcmil copper conductors typically have an ampacity of around 420 amps at 75 degrees Celsius. The 600 kcmil conductors have a higher ampacity, which provides additional capacity and reduces the risk of overloading the conductors. In terms of voltage drop, the 600 kcmil conductors will typically have a lower voltage drop compared to the 500 kcmil conductors due to the larger cross-sectional area. This can be an important factor in long service entrance runs. Ultimately, the selection between 500 kcmil and 600 kcmil conductors depends on the specific requirements of the installation, including the calculated load, voltage drop considerations, and local regulations. It's always advisable to consult with a qualified electrical engineer or inspector to ensure that the selected conductor size meets all applicable code requirements and provides adequate capacity for the intended use. Remember to also consider the termination temperature ratings of the equipment. Equipment is rated for certain temperatures, such as 60 degrees Celsius or 75 degrees Celsius. Conductors must be sized based on the lowest temperature rating of the terminations per NEC Table 310.15b16. In summary, selecting the appropriate size of service entrance conductors requires a careful evaluation of the calculated load, ampacity, overcurrent protection, voltage drop, and local regulations. The NEC provides a framework for ensuring the safety and reliability of electrical installations, and it's essential to follow these requirements to protect people and property from electrical hazards. Consider consulting a qualified electrician or electrical engineer, and always follow the local regulations. Now, let's discuss some additional factors that may influence the choice between 500 kcmil and 600 kcmil conductors for a 400 amp service entrance. Firstly, future load growth. If there is a possibility of future load growth, it may be prudent to select the largest 600 kcmil conductors. This will provide additional capacity to accommodate the increased load without having to replace the conductors later on. Secondly, conductor derriting. In some cases, conductors may need to be derrited due to factors such as ambient temperature or the presence of multiple conductors in a raceway. Derriting reduces the ampacity of the conductors, so it's important to take this into account when selecting the conductor size. If derriting is required, it may be necessary to select the larger 600 kcmil conductors to ensure that the ampacity is still sufficient to carry the load. Thirdly, parallel conductors. In some cases, it may be necessary to use parallel conductors to achieve the required ampacity. Parallel conductors are two or more conductors connected together to form a single circuit. When using parallel conductors, it's important to follow the requirements in NEC 310.10h, which include ensuring that the conductors are the same length, material, and insulation type, and that they are terminated in the same manner. Fourthly, aluminum conductors. Aluminum conductors are sometimes used in service entrance applications as a cost-effective alternative to copper conductors. Aluminum conductors have a lower ampacity than copper conductors of the same size, so it's important to select the appropriate size of aluminum conductors to meet the load requirements. The NEC provides ampacity tables for both copper and aluminum conductors. Fifthly, conductor insulation. The type of conductor insulation can also affect the ampacity of the conductors. Different types of insulation have different temperature ratings, which affect the amount of current the conductors can carry safely. The NEC provides ampacity tables for different types of conductor insulation. Sixthly, raceway fill. The raceway fill is the percentage of the raceway cross-sectional area that is occupied by the conductors. The NEC limits the maximum raceway fill to prevent overheating of the conductors. The raceway fill requirements can affect the size of the raceway and the number of conductors that can be installed in the raceway. Seventhly, ease of installation. The size and weight of the conductors can affect the ease of installation. Larger conductors are more difficult to handle and install, especially in tight spaces. It's important to consider the available space and the skill of the installers when selecting the conductor size. Eighthly, cost. The cost of the conductors can be a significant factor in the selection process. Copper conductors are typically more expensive than aluminum conductors, and larger conductors are more expensive than smaller conductors. It's important to balance the cost of the conductors with the performance and safety requirements of the installation. Ninthly, coordination with other electrical equipment. The service entrance conductors must be coordinated with the other electrical equipment in the building, such as the main breaker, panel boards, and transformers. The conductor size must be compatible with the ratings of the other equipment to ensure proper operation and safety. Tenthly, future expansion. If there is a possibility of future expansion of the electrical system, it may be prudent to select a larger conductor size to accommodate the increased load. This can save time and money in the long run by avoiding the need to replace the conductors later on. It is also important to consider the available fault current of the service entrance. The fault current is the amount of current that would flow in the event of a short circuit. The service entrance conductors and equipment must be rated to withstand the available fault current. The local utility company can provide information on the available fault current at the service entrance. Finally, remember to always consult with the local authority having jurisdiction or AHA to ensure that the service entrance installation meets all applicable code requirements and local regulations. The AHA has the final say in the interpretation and enforcement of the electrical code. In conclusion, the selection of service entrance conductors is a complex process that requires careful consideration of many factors. It's important to consult with a qualified electrical engineer or inspector to ensure that the selected conductor size meets all applicable code requirements and provides adequate capacity for the intended use.